So here I have the relevance problem of the Graham's law. So this problem involves a lot of calculating the rate of effusion of gas B using the Graham's law given of the effusion of gas A. Here I have the benefits of the problem. Most benefits of the problem are like benefiting predicting gas behavior, practical applications, scientific insights, analytic skills, mathematical skills, problem solving, and critical thinking. The development of the problem was created from scratch by applying Graham's law to a practical scenario involving gas effusion rates and molar masses. Also, it's not as difficult as it assumes to ideal gas behavior, uses manageable numbers, and avoid complex concepts beyond Graham's law. If you can see that. Here we have the uniqueness of the problem. Common Graham law problems typically involve comparing effusion rates of two pure gases with known molar masses. Also, an added complexity comes from combining Graham's law with concepts of mole fractions and gas mixtures. And here we have the Graham's law. Right here, the cutoff is the rate of effusion over the gas of rate of effusion of gas 2 equals the division of molar mass 1 and molar mass 2. Here we have the visual problem. Graham law states that the rate of effusion of gas is inversely proportional to the square root of its molar mass. Using gas, helium, neon, argon, and xenon, we calculated their relative effusion rates compared to helium. Also here you can see that the molecule of oxygen gas has an average speed of 12.3 ms at a given temp and pressure. Here we have the formula of the problem. The constants equals the molar mass specific of each gas. Units equals rate liters per second. Molar mass is grams per law, kilograms per mole. Graham law shows the lighter gases effuse and diffuse faster than heavier gases, which rates inversely proportional to the square root of their molar masses. And here you have R1 over R2 equals M2 over M1 divided. Here we have the solution of the problem. The molar mass values of methane and oxygen are 16 G moles and 32 G moles, respectively. Oxygen particles are twice as massive and methane particles, so methane will effuse at a higher rate. Here I have the Graham's law of effusion of at constant and the PT at the constant and PT at constant. Here are the different type of equations you can use. Here we have the verification of the problem. So here I did pick a problem. Which pair of gases contain one each effuse as twice as the rate of either pair? We can solve this problem by solving at a simplified problem. So if you would like to take a look at my problem, it can be simplified as well.
My name is Kylie Borm, and this is my part of the project. Relevance of problem. My problem states that a container holds 3 gases, helium, neon, and an unknown gas. Under identical conditions, the following effusion rates are observed. Helium effuses 3.2 times faster than gas X. Neon effuses 1.4 times as faster than gas X. Using Graham's law, calculate the molar mass of unknown gas X. This new problem builds on previous ideas by requiring students to calculate the molar mass of an unknown gas using the fusion rates of helium and neon. Early in the project, we explored that kinetic molecule theory as well as the concept of molar mass, which helps predict the particle speed. This problem connects theory to particle. Lighter gases move faster and heavier gases move slower. Calculations using Graham's law allow students to quantify these relationships by comparing the unknown gases to known gases. Benefits of problem. By being able to understand this problem, you can strengthen your comprehension of Graham's law by showing how a gas's molar mass affects its effusion rate. Solving it requires using basic calculating, and analytical skills. It reinforces the application of real-world situations and increases confidence in quantitative reasoning. After solving this problem, students can tackle more complex challenges like predicting diffusion rates, effusion rates under different conditions, and being able to calculate diffusion and effusion in chemistry and engineering. Development to problem. Developed by combining fusion rate data with the known molar masses of helium and neon to create the problem that requires applying Graham's law. You must use ratios, square values, arrange equations, and solve for unknown molar mass, which is more than a simple project would need. All the information that is needed is provided, and calculations stay within an average level. One difficulty in writing the new problem was making sure that I didn't repeat anything that the textbook already had. Uniqueness of problem. Unlike common textbook problems, which usually use one known gas and one effusion rate to this problem includes two known gases, comparing both to an unknown gas, making it more detailed. To differentiate the problem, additional steps were added, analyzing multiple rate ratios, choosing which comparison to use, rearranging Graham's law. To differentiate the problem, additional steps were added. You have to analyze multiple ratios, solve for unknown molar mass using realistic values, and choosing which comparisons to use. This problem goes beyond standard examples by requiring a multi-step calculation. You must evaluate this information, understand gas behavior, and then apply the law in a situation that mimics real laboratory analysis rather than just simple normal calculations. Okay, this is my chart. Significance of the data. Helium moves 3.2 times faster. It shows that extreme fast effusion because of its very low molar mass. Neon moves 1.4 times faster, slower than helium, but still significantly faster than an unknown gas, and the unknown gas moves just 1 time as fast. M1 is the molar mass of gas 1, M2 is the molar mass of gas 2, X stands for the unknown molar mass, which we're solving for. Helium effuses 3.2 times faster, neon effuses 1.4 times faster. The constant used in the problems, these are standard accepted values. The molar mass of helium, which is 4 grams per mole, and then the molar mass of neon, which is 20.18 grams per mole. Units involved, the grams per mole, unit of molar mass. Relative effusion rate is the unitless ratio. Ratios have no unit because they compare speeds directly. My solution for the problem, it's solved pretty well, I believe. The molar mass of helium is stated, the molar mass of neon. Given that helium effuses 3.2 times faster than gas X, we have, and then here's the formula with the numbers plugged in. Solve for the molar mass of gas X using helium data, square both sides of the equation, apply Graham's law to the neon and gas rate. Done down here. And then up here we have using Graham's law, plug in the numbers, solve for molar mass of gas X using neon data, square both sides of the equation, average the two calculated molar masses of gas X and round up, and you get mx equals 40.3 grams per mole. Verification for problem, check that the answer is reasonable. The calculated molar mass of the unknown gas is 40.3 grams per mole. This value is between the molar masses of two reference gases, helium and neon. Since gas X effuses slower than both helium and neon, its molar mass must be heavier than both. Okay, benefits of the problem. Okay, so the first one is the benefits of understanding the problem helps someone understand how gases X affect systems in those factories. It shows how different gases can spread, leak, or mix at different speeds. It also uses scientific reasoning and unit handling and some skills learned from this problem. The next one is development of the problem. Why is it just not coming? Okay, development of the problem. Okay, so I chose a manufacturing plant using two different gases, using two different cleaning glasses, then chose an original molar mass and a new effusion rate. The problem requires multiple steps. Because of these steps, it teaches real gas law reasoning. The numbers that are used help us keep the math manageable.
making sure the molar masses weren't too close together or too far apart. The next one is uniqueness of the problem. Okay, uniqueness of the problem. Okay, it uses everyday gases like oxygen, hydrogen, or helium. My problem asks you to identify which variable is missing, substituting original numbers, rearranging the formula. I added a realistic setting, both molar masses and one given infusion rate. My problem applies Graham's law to a practical scenario. Okay. The next one is the visual of my problem. Okay. So this is my graph of the problem, and it reads: the significance is the data points together how gas mass affects movement. It also is the relationship data is inverse. The next one is formula for the problem. So R1 is the rate of effusion. So R1 would be gas X, R2 will be gas Y. M1 is 58 gmol, and M2 is 24 gmol. Okay. Rate units, anytime based units. Solution for the problem. Graham laws compares the speed of two gases based on their molar masses. The next one is verification for the problem. Okay. The heavier gas is 58 gmol. It should move slower. The lighter gas, 24 gmol,